build the first habitat. It's can we build continuity across decades, repair culture, knowledge transfer, adaptable infrastructure, and community health. So the settlement survives leadership changes, economic cycles, and inevitable failures. And better yet, survives time. Interstellar is the emotional reality check. It links spaceflight to planetary instability, but it's honest about the cost, sacrifice, uncertainty, and the fact that physics doesn't care what we want. It also warns that under climate stress, societies can slip into a narrow survival mindset where imagination shrinks. So to me, those three stories point to the same practical truth. The future of spaceflight isn't only about engineering, it's civilization design. Closed-loop systems, maintenance, and human factors matter just as much as propulsion. And the deeper message is reciprocal. The discipline we need to live off-world, resource literacy, resilient infrastructure, and fair governance, is the same discipline we need to thrive on Earth. We're entering an era where the hardest problems aren't single-discipline problems anymore. They're systems problems: climate, resources, infrastructure, and human well-being, moving at the speed of technology, and it's moving fast. And overarching themes, I think, primarily come up with all of these and can be distilled into psychological reality, isolation, routine, maintenance, and the social dynamics of confined environments. The drama isn't always aliens, it's people and systems under constraints. And that's common here too. What sci-fi often gets wrong is the idea that technology alone solves everything. In real life, the hard part is integration. Supply chains, maintenance, redundancy, and the human factor. Even the best technical advances fail if they can't be repaired, understood, or trusted by the people living with it. That's why I love stories that show the unglamorous truth. Survival is logistics plus human psychology plus good design.
You've also mentioned literature shaping your thinking and that there are connections even with something as classic as Paradise Lost. How do you think Milton's work connects to the future of the space industry?
Paradise Lost is basically a warning about what happens when ambition detaches from responsibility. Ad astra per aspera. What happens when we reach for the stars, really? Milton is dealing with this infinitely huge theme. Beings with agency reaching for something immense, almost infinite. And the deciding factor isn't intelligence or capability, it's character. It's pride versus humility. It's whether power is used for stewardship or self-glorification. Sound familiar? So that maps directly to the space industry right now. We're unlocking capabilities that are genuinely civilization shaping. Launch cadence, global connectivity, Earth observation, planetary exploration, even eventually off-world infrastructure. But the technology isn't the whole story. The moral dimension is what incentives are driving it and who is accountable when the consequences scale up. In Paradise Lost, the fall isn't just a single dramatic moment. It's a sequence of choices where short-term desire overrides long-term order. In the space industry, the equivalent risks are things like moving fast without guarding the commonalities, treating orbit like an infinite landfill, prioritizing dominance over cooperation, or pretending Earth stewardship and space expansion are mutually exclusive. So I see space in this regard as a mirror for humanity. It amplifies who we are, both good and bad. If we bring our best human traits, curiosity, discipline, humility, cooperation, space becomes a force for resilience and knowledge. If we bring our worst, pride, extraction without responsibility, ends justify the means, we just export old failures into a bigger arena. The hopeful reading is that we get to choose the narrative. We can make reaching for the heavens an act of stewardship, protecting Earth, building redundancy for humanity, and designing systems on Earth and beyond that are fair, maintainable, and life-supporting. And honestly, that's part of what motivates ASTRAEUS, pairing ambition with ethics and performance. So progress isn't just faster, it's wiser too.
Hot take. Do you think we're living a simulation?
If I'm being honest, I don't claim to know. And I'm cautious about sounding certain on something that isn't testable in a practical way right now. I definitely believe there's a higher power, whether we call it God or the universe, and there is likely a series of automated systems in place. A simulation wouldn't be completely surprising in that context. So my answer is I'm open to it as a possibility, but I don't live my life as if it's the most important question. Regardless of whether we're living in a simulation or not, we still are living life and appear to have some degree of free will. Where a simulation is intriguing to me, though, is if it is a simulation, what are the constraints and parameters? Can we manifest or change outcomes, or is the program already written? Can we recode the system if we learn the language? What I do think is valuable about the simulation theory is what it highlights. We're operating inside a system with rules, physics, constraints, cause and effect, and we don't get to negotiate with those rules. Whether the universe is computed or not, The reality we experience behaves consistently enough that engineering, architecture, and science work. And there's another angle I like. The simulation question forces you to ask, what's fundamental information? Matter? Consciousness? It's a fascinating lens for space and technology because it pushes us toward deeper questions. What is intelligence? What is life? What does it mean to create new environments humans can thrive in? But here's where I land personally. Even if we were in a simulation, the moral stakes don't disappear. How we treat each other still matters. Stewardship still matters. Building resilient, life-supporting systems still matters. Maybe even more so, because it's the only reality we can act inside. So I keep it as a fun, open question, and then I come back to what I can work on, designing environments that are truthful to constraints, supportive to humans, and responsible in their impact, on Earth and eventually beyond. So if we indeed are in a simulation, I still want to be the kind of person who builds a good world inside of it, you know?
I remember you saying you wanted to be an astrophysicist before landing on architecture as a profession. What are your thoughts about Higgs boson? Nuclear fission?
You're speaking my language now. The Higgs boson is one of those discoveries that changes our understanding of reality, but it doesn't directly upgrade nuclear fission. The Higgs field helps give mass to elementary particles like electrons and quarks, which is part of why atoms in chemistry exist. But most of the mass of protons and neutrons actually comes from the strong force, binding energy inside the nucleus, not the Higgs itself. Fission works because the split fragments are more tightly bound, and a tiny mass defect becomes energy equals mc squared in action, basically. So the practical path to nuclear space power and propulsion is still materials, heat management, shielding, and reliability, not Higgs-level physics. But the Higgs matters in a deeper way. If particle masses were different, nuclear binding, and even which elements exist, could change dramatically. It's a reminder that spaceflight is built on the understanding of the universe's rules, and then engineering wisely within them. That doesn't mean we can't break the rules, of course, but we have to understand the consequences of doing so, which are not always so easily apparent without reverse engineering. So does the Higgs improve fission? Not directly. I mean, we're not tuning the Higgs field in a lab to get better reactors. Where the Higgs is relevant is more profound and more philosophical. The Higgs sets the masses of quarks, and those masses influence how nuclei bind. Physicists have shown that if those values were significantly different, nuclear physics and even which elements exist could change dramatically. So the Higgs is part of the deep reason the periodic table and therefore chemistry and life work at all. For spaceflight, the practical story is fission propulsion and space power are about materials, thermal management, shielding, and systems reliability. But particle physics research contributes indirectly through the technologies it pushes. Superconducting magnets, cryogenics, detectors, and big data systems, tools that show up in everywhere, from advanced energy concepts to spacecraft instrumentation. So the Higgs doesn't give us a new reactor knob necessarily, but it does remind you the future of space is ultimately built on understanding the deepest rules of reality and then engineering responsibly inside of them.
In the same line of thinking, what are your thoughts on dark matter, mining materials in space, and habitat design?
Oof, okay. Dark matter is a huge part of the universe. NASA pegs it at about 27%, and we infer it from gravity shaping galaxies and cosmic structure. But it interacts so weakly with normal matter that we can't realistically use it for propulsion or habitat power right now. Experiments like LZ keep tightening limits without detection. For near-term space habitation, the practical power story, of course, goes back to nuclear fission. NASA's fission surface power aims at approximately 10 kilowatts of continuous power for about 10 years, scalable with multiple units for the moon or Mars, which could easily power habitats long-term. Raw materials in space are the real MVP for long-duration habitats, though, because they change the economics and the physics of the problem. If every kilogram has to be launched from Earth, space living stays stuck in expedition mode. But if you can use local materials, you move towards something that can scale easily. The most important resource is water, especially in lunar polar regions, because it's not just for drinking. Water is life support, it's radiation shielding, and it can be split into oxygen for breathing and hydrogen oxygen propellant. That's why NASA is investing in mapping and characterizing lunar water. Missions like Lunar Trailblazer, for example, are aimed at understanding where the water is and what form it's in, particularly near the poles. Next is oxygen, because oxygen is both life support and an oxidizer for fuel. On the moon, oxygen is bound up in minerals and regolith, And NASA has highlighted progress extracting oxygen from simulated lunar soil at Kennedy's Swamp Works, moving toward processes that could be scaled. On Mars, the atmosphere is mostly CO2, and MOXIE proved the concept of making oxygen from that CO2 on Mars. So that we can't make air there, barrier is already gone. Then there's regolith as a constructed material. Lunar soil can be sintered or 3D printed into blocks, berms, landing pads, and shielding, basically using local dust as the bulk material, while you reserve imported mass for the high-precision parts, like pressure vessels, seals, electronics. NASA and others have showcased regolith-based 3D printing approaches using simulated material already. The big reality check is that ISRU is an operations problem. Excavation is hard. Dust is absolutely brutal on machinery, and most processes are power-intensive and need reliability. But the vision is clear. Once you can make air, water, shielding, and basic infrastructure locally, a habitat stops being a delivered object and becomes a system that can grow organically. And that's when living in space shifts from a heroic publicity stunt to a sustainable pathway.
If ASTRAEUS works, what changes?
I think it normalizes a culture of testing and iteration in the built environment, where performance is verified, not assumed. It helps architecture and aerospace stop talking past each other and start building together. Materials, habitats, workspaces, and community infrastructure designed for real constraints. Energy, water, carbon, heat, risk. If it succeeds, the ripple effect is bigger than one campus. It's a model for how we can create places that can adapt as fast as the world is changing.
Last question, as we are just about out of time. In your opinion, what's the most uncomfortable truth about the future of design?
The uncomfortable truth is that climate and technology are moving faster than our delivery models, our codes, and sometimes even our professional habits. If we keep designing the way we designed 20 years ago, we'll build tomorrow's problems at scale, and that scale is huge. ASTRAEUS is an attempt to respond with a different approach. Systems thinking, measurable performance, modularity, and interdisciplinary teams. So we can keep up with reality and still build places people actually want to live and work in. So our hope with ASTRAEUS is to help normalize a new way of building. Interdisciplinary by default, performance verified, and human-centered under real, not simply theoretical, constraints. Because the future isn't just something we predict, it's something we design. And I'll end with an invitation. If you're an architect, engineer, scientist, maker, or investor who cares about resilience, climate resilience, operational resilience, and human resilience, this is a conversation I want to have with you. Let's talk. We don't just need new technology, we need new ways of collaborating. ASTRAEUS is a prototype for that.
Thank you so much for speaking with us today, Taylor. In our next video, we'll be speaking with an industrial designer and learning about how product concepts are developed and produced. Thanks for watching, and make sure to follow us if you like what you see.